And so by using our chemical potential framework on the water species in the system, we were able to derive a relationship between the mole fraction of water in the vapor phase and the mole fraction of water in the liquid phase. And this is known as Raoult's law. Let's now apply our chemical potential framework to CO2. So a couple of things I want to say about CO2 before we go through the different steps is that when we're going through the water, or at least for CO2, the temperature of this problem is 298.15 K. And if we're dealing with pure CO2, we know that the vapor pressure of pure CO2 at that temperature is 248 bar, right? And that's much higher than the 21 bar we're dealing with in the problem statement. And so essentially what this tells us is that CO2 does not even exist as a liquid at the conditions of the problem statement. Right? So if you just had CO2 alone at 298.15 K, it would all be in the vapor phase. There would absolutely be none in the liquid phase. But because we're dealing with a mixture, we will have some CO2 that does dissolve in the liquid phase or in the water. And that's just due to the entropy of mixing. It increases the entropy of mixing. All right? So the idea is that our entropy of mixing term, xCO2 ln of xCO2, right? This entropy of mixing term in the Gibbs energy, right? If we increase the mole fraction of xCO2 ln xCO2, it will increase the magnitude of this term, right? And so, also, at the same time, increasing the mole fraction of xCO2 will decrease the chemical potential due to this term, right? And so there is some benefit for some of the CO2 dissolving in the mixture, right? But we have to remember, one of the assumptions we're making in this problem is we're dealing with a dilute solution, right? If the mole fraction of CO2 starts to get too large, then that assumption breaks down. Okay? Right? And then the system suffers what's called as an energy penalty, like the Gibbs energy would start increasing and making the dissolution of the CO2 unstable. Okay? All right, and so when dealing with a CO2 water system, it's really only ideal if the CO2 is dilute. Okay? And so with that in mind, we need to account for that in our chemical potential analysis. All right? And so we're going to apply the chemical potential analysis framework to the CO2 species. Okay? And so, To do this, we'll apply the same steps we applied before, starting with step 2. Because step 1, we just wrote out, defined our equilibrium criteria. And so for step 2, we want to write out the chemical potentials for the CO2 species. And so in the vapor phase, which CO2 could readily exist at, the chemical potential for the CO2 is going to be our standard state chemical potential at some temperature, and then the ideal gas entropy mixing term, which is this. And just like we did with water, we could write the standard state chemical potential for the pure vapor, and we could also rewrite the partial pressure in terms of the mole fraction. Okay? Alright, and here, the standard state chemical potential, right, because CO2 readily exists as a vapor at these conditions, this will be the Gibbs molar energy of pure CO2 in the vapor phase. For the liquid phase, things are a little bit trickier. So our liquid chemical potential for CO2 is equal to some standard state plus RT ln of x CO2. Right? And so here, for the standard state chemical potential, we're going to write it in terms of CO2, pure liquid CO2, okay, plus RT ln. The tricky thing here is, as I mentioned before, at a temperature of 298.15 K, pure liquid CO2 does not exist. All right? So that means this standard state chemical potential we're defining, because the pure liquid CO2 is not stable at 298.15, that means the standard state chemical potential is not actually equal to the CO2 liquid phase. Right? And so, the way to think about it is this mu standard state for CO2 is actually some sort of hypothetical chemical potential, or hypothetical value, for the pure liquid CO2 if those molecules had the same interactions with each other as that they have when they're interacting with water molecules. So it's like it's only, or like they're only, or I guess the liquid acts like it's only interacting with water molecules. Okay? And so the reason we're kind of putting in this hypothetical value is this will allow us to still use our chemical potential framework, or the ideal solution framework. Okay? Alright, so with that in mind, let's move on to step 3, where we're going to apply our equilibrium criteria. Alright, so at equilibrium, the chemical potential of CO2 in the vapor phase is equal to the chemical potential of CO2 in the liquid phase. We'll plug in our chemical potential equations. Pure sum T plus RT ln of y CO2P over P naught is equal to mu CO2 standard state of the liquid plus RT ln x CO2. Okay? I'm now going to rearrange the equation so it looks like this. So we have RT ln of y CO2 P over P naught, which is equal to RT ln of x CO2 plus mu CO2 naught L mu CO2 V pure. Okay, so we have this statement here. And we have our two standard state chemical potentials here. When we're dealing with water, the liquid and the vapor standard state chemical potentials were equal to one another, right? And that's because they represented the molar Gibbs energy, and at equilibrium, those molar Gibbs energies of both phases were equal. But with CO2, as I mentioned, while the vapor phase is stable, the liquid phase is unstable. And so as a result, the difference between these two terms here, unlike with water, these terms, when we subtract them from one another, that's not going to be equal to 0, right? And that's because the hypothetical liquid standard state chemical potential is not equal to this. And so this is not equal to this, because for the vapor, that is equal to the molar Gibbs energy of pure CO2 in the vapor phase. Okay? So that term doesn't go away. So what I'm going to do instead is I'm going to rearrange the equation like this. Y CO2 P. So I took the exponential of both sides. Okay. We have x CO2, right? And on the right-hand side, I'm going to have P naught exponential mu CO2 L minus mu CO2 vapor pure divided by RT. All right? And so on the right-hand side, what we have is some sort of standard state pressure multiplied by this exponential term. Right? And so essentially we're going to have units of pressure, and it's going to be modified by this exponential. Okay? And if we compare this, back to Raoult's law, with Raoult's law, we had y CO2P is equal to liquid mole fraction times P sat. In this case, we also still have a pressure, right? And so the way to think about this right-hand side is essentially it's some sort of effective vapor pressure. For our species, our CO2, in the dilute limit. Okay? And this effective vapor pressure has a name, and that name is the Henry's law constant. Okay? And so what the Henry's law constant is, it's just a hypothetical saturation pressure. That's all it is. Okay? All right, so now that we've defined what the Henry's law constant is, I'm going to rearrange this equation into this form. The partial pressure of CO2 is going to be equal to y CO2 times P, and that's equal to x CO2 times H. This equation, since we're using a Henry's law constant, this equation is Henry's law. Okay. Alright, so once again, using our chemical potential framework, we developed an equation that allows us to relate the composition of the vapor phase to the composition of the liquid phase. But in this case, we're describing a species that's only sparingly soluble in the liquid phase.